So continuing on using the previous theoretical ideas that we've developed, let's go through and see how to solve the general first order system of linear ordinary differential equations using a generalized variation of constants formula. Assume that A of t is a continuous, so an n by n continuous matrix function and that B of t is an n by 1 continuous vector function on an interval I. And that capital Phi is a fundamental solutions matrix for the homogeneous problem. Then the general solution to the initial value problem star is given by the following. And I'll rewrite the initial value problem down just so that we have it down. Like we said before, it's psi of t is equal to the homogeneous general solution plus the inhomogeneous particular solution where the general homogeneous solution is the fundamental solution matrix of T multiplied by the inverse of the fundamental solution matrix at T naught multiplied by the initial condition vector as I naught and xi p of t, a particular solution, is the fundamental solution matrix phi of t times the integral from t naught to t of the inverse of the fundamental solution matrix at S times B of S ds. And I'll go through and verify why this is the form for the general solution in the next page of notes. But I want to note, make a very important note here, this is exactly what we get when we go through and do the single ordinary differential equation variation of constants formula. Right, so this formula can be titled, this theorem can be titled variation of constants. For first order systems of ordinary differential equations. And I'll show this in the following. So note that this formula in ND is saying that the general solution to psi of t is equal to this which is the homogeneous solution, the general homogeneous solution, plus this psi p of t which is a general particular solution for the particular solution, a particular solution to the differential equation. You'll recall that in 1D, the linear first order differential equation x prime is equal to a of t times x plus b of t. We had that x of t was equal to e to the integral from t naught to t of a of tau d tau times x naught plus e to the integral a of t dt times the integral from t naught to t of e to the integral from t naught to t, or t naught to s, of a of s, a of tau, d tau, multiplied by b of s ds. And the similarities between these two formulas should be very, very, very apparent, right? What we're seeing here is that for the single differential equation, single first order differential equation, our phi of t which in general in ND is a matrix, is just this function of t, e to the integral from t naught to t of a of tau d tau, which if you plug in the value at t naught is just equal to e to the 0 or 1. So this value, the value is just going to be 1 over e to the 0 or 1 over 1, which is 1. And this should be a negative sign right here as well, because this is then 1 over e to the integral from t naught to s, which is the algebraic inverse of this function right here. So if you want to rewrite your formula from before, you can rewrite this as x of t is equal to phi of t times 1 over phi of t naught times x naught plus phi of t times the integral from t naught to t of 1 over phi of s times b of s ds. This is for the 1D scenario. But you can hopefully clearly see that this formula is directly related to the general formula that we found for systems of first order differential equations. This is really remarkable. It's an incredible generalization, and we're going to see in the next few lectures how to go through and use this to our advantage, both to apply to linear systems and to nonlinear systems. But let's just go through and verify that this is giving us a true solution to our homogeneous and I should say the general ODE star. So if we look at the derivative of psi h, this is going to be the derivative of this function, which is a constant vector, is a constant matrix times a constant vector. So the derivative of this function is going to end up just being the derivative of psi of t multiplied by psi, or phi of t, the derivative of phi of t multiplied by this constant matrix times this constant vector. And because phi of t is a fundamental solutions matrix, this is the same thing as A times phi of t times phi of t naught, the inverse matrix, times I naught where we can express this as A times phi of t times the inverse of phi of t naught times I naught, which is just equal to A of t times psi h. And really want to indicate here that A here is a matrix function of T. So in general, this works not just for constant matrices, but for more general, function coefficients that are functions of the independent variable. And this also satisfies our initial condition, because when you go through and look at psi h of t naught, you're going to be getting that this is going to be equal to phi of t naught times the inverse of the matrix phi of t naught times xi naught, which is just equal to the identity matrix times xi naught, which is equal to xi naught. And we also want to verify that xi p is a particular solution. And this is a little bit more challenging because you have to go through and take the derivative of the product, matrix product of this matrix with the matrix phi of t with this matrix right here. But this isn't too bad when we go through and generalize the product rule. And the product rule does, in fact, generalize very, very nicely to matrix and vector functions. So this derivative will be phi prime of t times this integral plus phi of t times the t derivative of this integral. And using the fundamental theorem of calculus, then this is going to be equal to the integrand evaluated at t, which will be phi of t inverse matrix multiplied by b of t. And so psi p prime, well, phi prime is going to be a times phi of t times this integral plus the matrix phi of t times the matrix phi inverse of t times b of t which is the identity matrix, and this will be A times psi of t times the integral from t naught to t of the inverse of the matrix psi of s times B of S plus the identity matrix times B of S. And in the parentheses right here, the first parentheses, this is just our form for the particular solution itself, xi p. So we have that xi p prime is equal to a of t times xi p plus b of t. Oh, and this should be b of t right here. So this does satisfy it is a particular solution because xi p does in fact satisfy the differential equation star. In the initial condition, if you plug in t naught here, you get the integral from t naught to t naught, which is the integral from a constant to itself, which is equal to 0. So this will be xi of t multiplied by the 0 vector which is just equal to 0. So there's the 0 vector, which means that the general solution at t naught will be the homogeneous solution at t naught plus the particular solution at t naught, which is xi naught plus the 0 vector, which is just equal to xi naught. So this is really incredible. This gives us a full, generalization of the variation of constants formula, but to first order systems of differential equations. And in the next few lectures, we'll go over how to deal with this specifically for constant coefficient systems and then maybe for more general systems as well. But thank you very much for tuning into lecture today. I hope you had a great day.